Gracias, Mónica, por la presentación. Bueno, yo no sé hablar en castellano y gallego, es un poco difícil para presentar una palestra técnica, pero voy a hablar en inglés. Si hay algún problema, me paran y yo voy a intentar pasarlo para portuñol o algo así, ¿no? So I will switch to English now, and thank you very much for the invitation, for coming here today to present. I have mainly two talks today. One is on metrology developments for future wireless telecommunications. So my idea today is to present you what are my personal views in terms of what is the future in this area of radio communications, and when I need to measure them, what are the challenges we have there. And the second part of the talk, Monica asked me to focus a little bit more on nonlinear distortion. So I will present you from a nonlinear point of view, how can we measure a device from a nonlinear point of view. So this, hopefully in 2 hours I can pack everything here. The first talk today, I will briefly give you an history and context of what I'm talking about, what we are working on. I will then show you some challenges in software-defined radio design. I will show you some challenges on an emerging tech area that is wireless power transmission and energy harvesting. Then I will show you some existing metrology instruments that we can use to characterize those systems. And then I will talk briefly about mixed domain systems. What are mixed domains from my point of view? There are two mixed domains in these areas. For software-defined radio is analog and digital. For wireless power transmission is RF and DC. So RF on one part, DC on the other part. So I normally start my talks with these two guys. Up to now, I normally start my talk with this guy, which for me is one of the most challenging persons in the world, because actually I say to my students that this person was the first engineer in our field. Why? Because we have Maxwell, we have Hertz, you know all those names, but they were mainly physicians, so they only create knowledge. This person here creates money, so it transforms knowledge into money, and this is actually my view of an engineer. He has to put the economy working, and for us, Portugal and Spain, this is very important now. So, and what I say that I normally talk about this guy, because these two guys, this is Marconi, as you know, this is Tesla, and these two guys are more or less, they appear more or less on the same time. And they actually create two different concepts from my point of view for radio systems. Marconi, the main idea of Marconi was to start creating a communication system. He wants to communicate mainly at that time was between the boat and the shore. That was the main thing. He wants to communicate with boats, because before Marconi, I don't know if you know, how can I communicate with a boat? Do you have an idea? If I want to communicate with a boat, how can I communicate with a boat? Any ideas? No ideas? What do you think? Light? It can be if we are in the shore. Smoke? If you are in the shore. But if I'm in the middle of the ocean, like Colombo, how can he communicate with Spain? Don't you have a clue? With pigeons was the only way he can. But it was only in one direction, not on the other, because the pigeon doesn't know where the boat is. So he can send the pigeon to Spain, but we don't have a return channel, okay? And Marconi, that was the main thing. Okay, I want to put boats communicating, and actually the Marconi company, the first equipments they built was for using in boats, okay? So Tesla, at the same time, he also wants to build a radio instrument. He also wants to use radio frequency signals. But the idea of Tesla was completely different from Marconi. The idea of Tesla was not to start a communication, was to send energy via the air. So he envisaged that I can power up all the devices you have in your house using radio frequency. So he wants to send energy wirelessly. And that was the main idea of Tesla. Actually, he built up this tower project, the Vandercliff Tower project. There were a lot of money put it there because he wants to create a huge tower that can send energy to the air, and then in each house you'll have an antenna to switch up your lamp or other devices. So it was a different concept. And actually it was curious that at that time the technology was not so advanced, so the most important thing Tesla did at that time was a circus experiment. You have to see the Tesla movie because you see that very... So a magician thought, okay, this is nice, I can make some kind of magic and start to have power, sending power all over the circus, and people was crazy on that at that time, but it was mainly that scenario. And of course, those were, from my point of view, the first two crazy guys that start these ideas. But then you have other crazy persons. So here you have a radio mobile in a horse door. This is this was one of the first mobile phones. Why? This is the antenna you see there, this is the headphones, and the radio is here. And this guy was an Hollywood guy that goes around, and he normally goes to the director and he goes to the actor saying, you have to do this, and he goes to the director. So he get fed up to start moving around the Hollywood stage, so he asked some colleague, can you build me something? They had a lot of money, of course. So they build this, so the guy doesn't have to go to the director asking for instructions. So here I show you military applications. I show you also, this was presented in the, I think it was Munich Fair, where this guy has an antenna there and the loudspeaker, so he was sending music all over the place. So, and this is to show you that most of the advanced ideas start with these guys that think, okay, can we do this? Let's try. Let's see what comes out from here. Let's see what we can build. And actually, if you look from a radio communication point of view, you had the Marconi long distance communications. Actually, Titanic has a Marconi radio inside. They claim that if they don't have a radio inside, a Marconi radio, everybody will die. So they save some because they send an SOS to the air. Then you start to have broadcast radio that from a social point of view was very important. Then you start to have TV. As you know, it was extremely important to go to the society level. Then in the 80s, we start to have mobile phones. I normally say that here we start to mimicking God because we start to be omnipresence. Okay, so now if you want to talk with your girlfriend, you know where she is, you call her. And if she doesn't pick up, you say, something is happening. Okay, so this is a very big problem in terms of society. And then of course, then you have data communications where we start to interconnect people. So everybody, sometimes it's even faster to receive an email from someone than to phone to that person. Of course, the problem with this was that the spectrum started to be crowded. So this is the spectrum allocation in the United States, and you have all frequencies are used, and they are giving a lot of money to governments also. This is, and I believe in Spain you have the same problem. But on the same time, something strange starts to appear, because you can hear me? Yes, sorry. You have a phone, and you use the phone, and we see it. I don't have an image here, but if you see the phones in the last, let's say, decade, you have phones like this that comes down, and now we are going up again. Okay, so the phone, let's say the regular GSM phones have a battery for 1 week. This phone has a battery for less than 1 day. So a problem that starts to be very, very important now is energy. Energy starts to become more important than radio communications, in the sense that we already have the radio communications. So what is the problem? The problem is that each night I have to pick up this phone, go to my bed and put a connector here. I have to connect this to charge the battery. And actually I'm showing you here, we don't see it very well, but my kids, they are scouts, and they have gone to a scout camp this summer. And I see in the scout camp that you have a house to sell food, house to sell water or to give water, and you have these houses that says power zone. And I said, what is a power zone in the middle of a scout camp? And I go there, and what is the power zone was a huge number of connectors to power up the mobile phones for each scout. They have 500 phones being charged at the same time because it was a huge camp. It combines old Portuguese scouts. And it was curious that you start to have a very, very, very big problem, power to the phones. So this is where I believe the new concepts of Tesla that were sleeping for decades or more than 100 years start to appear now. That is wireless power transmission, or if you want, energy harvesting, so that I can power this without thinking of charging the phone. That's the main idea. So if you look from a radio power transmission point of view, so actually Tesla proposed the first experiments. Then in the military you have the crystal radios, where you have galena radios, so actually radios that you don't need batteries to use those. Then there are some crazy ideas that appear in the US and Japan, and now there are a lot of people working on this. That is, can we collect energy out of space and send energy to ground via radio? So these are exploring these ideas here. Then in '64, this guy, William Brown, he powered up this. This is like an helicopter. You see, this is a base and this is the wings. So it's like a helicopter, and he powered the helicopter from ground. So he has a coil in the ground, an helicopter, and the helicopter is being powered from the ground. And he also was on one of the inventors of what it's called the rectenna, which is an antenna that converts RF signals to DC signals, or to energy if you want. And of course, this is the most, let's say from a society point of view, the most well-known system that uses radio energy to power up the electronics here. So these RFID are completely passive, no battery at all. They don't have a battery inside, but they can use the radio signal to wake up and send some information back. So I normally say that the next frontier is what I call the wireless thing. So we are now moving in two, let's say, directions. Low bit rate, that is low power, low complexity, and I'm talking about remote controllers, I'm talking about RFID tags, and you are moving on another direction, which is high bit rate, which are high power, high complexity systems. Then we should combine both of them. I normally put this here because I think this is one of the first ideas that combine both of them. This is a trouser, okay, and this is a washing machine. And the idea is that I have an RFID here that can communicate with my washing machine, and my washing machine can decide what to do with that kind of... This is being developed at this point, and I don't want to charge the battery of my trousers every day, of course. I don't want to have a closet with connections, okay? So the idea is that this is passive, and this is some kind of reading mechanism of these trousers and have high data bit rate, so it can update the information, it can go to the internet, show, okay, this is from this brand, so the best way to wash this trouser is like this, and so on, and we can have that information very, very fast. And actually, before I move further, in December, Nokia is going to put in the market a new phone that actually will cut the wire for powering the phone. So this that seems like a new and some, let's say, academic ideas, it will become a reality in December. When Nokia, what Nokia did was not very, nothing important. They put a coil inside, and they put a coil in your table. So when you put the phone in the table, it's charging. So it's no big deal, but it's completely different because sometimes you go home and you have to search for your cable and connect the cable, and this spends 3 minutes, and in this stress time, 3 minutes is a lot. So imagine that you go home and you do this, and it's charging. So this seems simple, but I believe it's going to be a great thing, because what they are trying to do now is to make collaborations with IKEA and big brands, so that your table could be the charging mechanism. So you don't need to do nothing. You connect your table to the wallet, and that's it. And they are doing this now for mobile phones. Hopefully it's going to be a big thing, but they are also doing it for kitchen utensils. So I have my toaster, or I have other devices there. I don't need to power them to the wall. I have a coil on my kitchen, and I only put devices on top and they charge immediately. So this is becoming and will become a very, very huge activity. So let's return to our ground. So we are, and I believe you'll be radio engineers, or hopefully, and from a radio engineer point of view, I think there are two challenges. One is the software-defined radio, so the high bit rate. What is software-defined radio from my point of view? Software-defined radio is, in terms of the front end of my radio, I have an antenna, and I don't know, probably you know this, but at this moment, if I want to build a radio, I have an antenna, I have to have a down converter, I have to have some kind of super heterodyne system, I have to have an IQ demodulator, an ADC, and so on and so on. So what is the concept of software-defined radio? An antenna, a filter, a low noise amplifier, and an ADC. So goes immediately to the digital domain, and on the other side is the same. I have a digital to analog converter, power amplifier, sometimes I don't need a power amplifier, and antenna. So this is the concept. Why is this important? Because if I have a digital signal here, I can demodulate everything. I can do it with software, okay? And this, only to tell you, this seems a new thing. It's no longer a new thing. I see in the European Microwave Conference last week, they are already selling systems like this with 200 megahertz bandwidth working at till 4 gigahertz, which means that it's already there. We can already buy something like this. And I normally say to my students, so my mobile phone of the future is going, when I buy it on the market, is coming virgin, like a computer. If you buy a computer, it doesn't bring nothing with it. So you have to buy the operation system. So here it will happen the same. You have to buy an operation system for him. It's already happening. You have to buy if you want Android or if you want Windows and so on. But it's only at an application layer. This is more than that. This goes to the physical layer. So it says, okay, I buy the version phone, let's say, and now I want to be a TV. So I connect to the internet and I bring the TV receiver here, and it becomes a TV. I want it to be GSM based, so I go to the internet and I install GSM. I install LTE, I install whatever you want. So somehow you can install different things in this scenario. So this is from a point of view of software-defined radio. The other point of view here is on the RF to DC. What is RF to DC? Is I want to catch radio frequency signals and I want to convert it to DC. I want to power up my devices. And here I show two simple circuits. The most simple circuit is a simple rectifier like this. Okay, you have a diode, or you can have, this is normally what is used for energy harvesting. What is energy harvesting? This concept is if you come here to this room and you monitor the energy around, you see that you have Wi-Fi, GSM, probably TV, FM. So can I collect all this energy and power up something? So I don't know if we can, but this is the idea. And these are the main simple circuits for that. And here I have the RFID type of circuit, where you have the same rectifier, but also you have a voltage multiplier, so that we can power up some kind of integrated circuit to do something. And in this case, we are mainly talking about wireless power transmission. What that means, it means that you generate energy, you send the energy to your device. It's different from the concept of energy harvesting. Energy harvesting, I don't know from where the energy comes from. In wireless power transmission, your system is designed to power up a specific device in a specific area. So let's talk briefly about software-defined radio. So what I was saying is that we can have different systems there, we have our radio, and actually by changing the software, I can change my radio. So it's mainly a software problem. And the main, from my point of view, where we are heading in this area, we are heading in two directions. One is what it's called bandpass sampling receivers. I don't know if you have talked about this or not, but this is a very, very, very interesting thing, because actually what we do here, we have a sampler here. You know what is a sampler, right? So what we do is we use this sampler that's very high frequencies so that we can actually receive different Nyquist sounds. So I'm entering a lot in signal processing now, but actually I don't need to follow the Nyquist rule where I have to use the double frequency of my useful signal. I can use actually different Nyquist frequencies higher, and this is one of the possibilities that we are envision for receivers. But at the transmitter part, and I know that you have been talking about power amplifiers, the transmitter part for me is most interesting one, because actually here what we are talking about is you bring digital signals up to a transistor that can be switched. Okay, so it can be a real CMOS, if you want, transistor, or a real CMOS transceiver, and actually what you have to do afterwards is to filter this out, and you have your signal at the air. So you bring your digital up to the antenna, and the only thing that is in the middle is a filter. Okay, this is the problem at this moment, is that is not very efficient. Okay, we are spending a lot of power there. That's the only problem. But we already have systems working with like this up to 901 gigahertz. So we can actually build everything on an FPGA, digital based, have a switched power amplifier, and then an antenna, and goes to the air. So it's possible. So this is the concept of, I will not spend a lot of time here, but this is the concept of bandpass sampling receiver. So actually you sample your signal, but what you'll see is that you have a band, another band, another band, another band, and the bandpass sampling receiver, what it does is like a folding. You see, you fold all these bands and they all jump on top of each other. So this is a problem. You need to have very strong filters, very high dynamic range, very good jitter. You have a lot of problems to build a radio like this. But this is actually one of the possibilities, and we believe this is actually the possibility to build a real software-defined radio in the future. I will not spend a lot of time. I will talk about this later on. So, but imagine that you have, this is the spectrum, okay? You have frequencies all over the spectrum. So a bandpass sampling receiver has a problem, because since you are sampling at a lower frequency in the Nyquist zone, you'll have overlapping of different spectrums there. So there's a huge problem to resolve here that we have to see how can we overcome these problems, but I will talk about this later on. The other problem that we have with software-defined radios now is a dynamic range. Why dynamic range is a problem? Because you know what is dynamic range? Have you heard about dynamic range? So dynamic range, from my point of view, is the difference between the maximum power my receiver can receive, let's say, and the minimum power it can receive. So it is this range. This is, from my point of view, what it is. And what we normally do in a receiver, we put here what it's called a variable gain amplifier. Okay, so what happens if your signal is a small signal? You increase your gain within certain limits, of course, and your ADC can capture your signal. If your signal is a very strong signal that will saturate your DC, what you do? You reduce the gain and you capture the signal again. So this is okay for today's systems. Why? Because my radio is a GSM radio. My radio is a UMTS radio. My radio is a TV radio. It's not a software-defined radio in the concept that it can be everything. So I want to receive everything, and I want to discriminate what I want. So this is the idea, of course, the utopic idea at the moment. But in order to do that, what is the problem? The problem is that you're going to have at the input of your receiver a very high power signal, and a very small power signal at the same time. So if you do variable gain amplifier, in Portugal we say that if you have if you cover yourself, you cover your feet or your head. So you try to cover your head, you let feet out, you try to cover the feet, you have your head out. So here is the same. I cannot use this because I cannot catch, let's say, the two signals at the same time. So this is another problem to resolve. How can we increase the dynamic range of these devices? This is a very big problem and is being dealt at the moment. And more important than that, we are also looking to what it's called an adaptable RF transceiver. So we are looking to some concepts as what they call spectral aggregation. What it is, at this moment, you have a channel, GSM channel, or you have an LTE or 3G channel, you have a 4G channel, you have a digital television channel, but it's small. It can be wide bandwidth, but they are condensed in spectra. With a cognitive or a software-defined radio approach in the future, what I will look to the spectra and I said, okay, I have a hole here, a hole there, and a hole there, so I will design a signal that is something like here, you see? Spectra here, spectra there, spectra there. So you have spectra all over the place, and you want to capture everything. And this spectra is very problematic for my receiver, but because as you'll see in the second part of my talk, it can create high peaks in the time domain. And what will happen with high peaks? It will saturate your receiver again. So again, you have a dynamic range problem. So this is becoming a very, very, very big problem in this sense. So wireless power transmission challenges. So I said, you have two concepts. One is energy harvesting. So the idea is that I can harvest energy from different radio transmitters and I can convert this in energy for mobile phone. Actually, if you look, my mobile phone is here, is receiving GSM signals and wasting the energy, is not using the energy for nothing. If I can store that energy that is arriving to the phone, I can have a better life of my battery somehow. So the main problems here is that for wireless power transmission, for instance, you have a power amplifier here. In this case, I call it a DC to the RF converter, which actually is a power amplifier. You convert energy from DC to the RF. Then you have your antenna, your air interface, the receiving antenna, and then you have your RF to DC converter. And what are the challenges here? Increase the efficiency here and increase the efficiency there so that we don't waste energy. That is the main challenge we have here. And so actually, my main problem here is to increase the overall efficiency on these systems, okay? So I will not spend a lot of time here. So I already show you this. So this is the single diode detector. This is the N-level voltage multiplier that we normally use in RFIDs. And the challenge here is how can I design these circuits so it can convert the maximum possible RF energy from this side to a DC energy for my load. This is the main challenge in my problem here. And in order to do that, and this is where I want to come, in order to optimize these circuits, in order to optimize dynamic range of software-defined radios, a very, very big problem is how can I extract nonlinear models? Why? Because you see, here you have a strong nonlinear device. It converts frequency to another frequency. In this case, it's RF to DC. In the software-defined radio, when you start to saturate your device, it becomes nonlinear in this sense. I will show you later on what is a nonlinear concept, but actually, if you have good models in your simulator, you can design and you can improve these circuits. If you don't have good models, it's a trial and error Tesla concept, so I try and test what happens. So this is actually one of these very important problems, is how to model. But for modeling, I normally say to my students that we are not networking guys. I hope no networking guy is in the room, because we normally look to reality. MATLAB gives everything you want. ADS, Microwave Office, they give what you want. Why? Because it depends on the model. And if you put a simple model there, you can change the model, okay? The problem is when you go to the lab, you measure it and you say, no, it doesn't mix, okay? That's normally what probably your professor already told you, that when you want to build a good oscillator, you're going to build an amplifier, and you want to build a very good amplifier, you're going to build an oscillator. So this is what normally happens. Why? Because our models are limited in the sense that they don't represent the overall state space in that sense. So, but for doing good models, I need to go to the lab and I need to extract, I need to measure the device. I need to see what my devices or what my systems are behaving. I need real data, not MATLAB data, because we are supposed to build real systems in the real world. And this brings me, and I can move this brings me, I will move this fast, this brings me to what can I do in the lab. So what can I use in the lab to extract these models? So I will move first with the instrumentation, and I will start with the more important instrument in my lab, which is a power meter. So I want to go to the lab and I want to measure power. So this is a power meter. Power meter, most of the time, they use some kind of detector, thermistor, thermocouplers, whatever. They use a detector to measure the power, and then actually they have an algorithm, so something that you can use here and display the value. So this is the main concept of the power meter. Okay, I will not go to this part, but if you look to a power meter inside, a power meter is exactly like an RFID. It's an RF to DC converter, nothing more than that. Why? Because I want to convert RF energy into a DC value that I can measure and I can say, okay, this DC value is 1 watt, 2 watts, and so on. So one of the, if we look to a diode probe, let's say, of a power meter, this is very simplistic, of course, but it's nothing more than this, a diode and a capacitor. So capacitor, and you have here a load, of course. This is a filter to filter out higher components, and this diode actually is a rectifier. So if you approximate this rectifier, which can be given by an exponential and so on, but if you approximate this with a Taylor series, you actually, I'm cutting the Taylor series here at the second order, you actually see that if you put a sine wave at input, what you're going to have at the output is a component at sine wave and the square of that sine wave. If I filter out with this part here the higher frequency components, what you're going to have at the output is something like this, K2A squared over 2, which is the power at input. So if you calibrate this, you immediately have the power of this. Of course, this works for a certain amount of power. If you increase a lot of the power, then you cannot truncate this here. You have to include third order, fourth order, so you should have a bigger polynomial to approximate your function. That is usual. And if you do this, actually, if you calibrate, you have a pretty good result. So what we found, and when I say what we found, is us and Monique and Alex, what we team up, and we found that a power meter calibrated with a one tone doesn't work with other signals at input. So if you use a GSM signal at input, if you use, a GSM is not very bad, but if you use, for instance, a 3G signal at input, if you use a digital TV at input, forget power meter readings, because it's going to give you bad results. So I will show you later on why this is happening in this sense. So another instrument that you can find in the laboratory is a network analyzer. I know that Hageland has been here talking a lot about this network analyzer. So actually a network analyzer can measure analog signals, input, output, can give you frequency behaved signals, can give you measurements when you change the power. So it can give you a lot of this information, but as I say here, this is very good, but doesn't measure digital signals. So if you have a software-defined radio, the input is analog, the output is digital. This is irrelevant, okay? If you have an RF to DC converter, RFID, the input is analog RF, the output is DC. I cannot put DC inside, it doesn't work. Okay, so the network analyzer is good for traditional RF signals where you have input and output at RF. Another instrument, this is quite interesting, is a spectrum analyzer. Spectrum analyzer actually can allow you to measure spectra, but again, no digital signals and no DC. Why? Because sometimes you have here a DC coupler that doesn't allow you to have DC inside. Okay, so spectrum analyzer is a problem in this sense. Well, oscilloscopes are good, but they have limited dynamic range, as you probably know. So you have a lot of noise coming in these digital scopes or analog scopes. This is another instrument that radio engineers don't use. It's called a logic analyzer. So it gives you the bit stream at the output. But with software-defined radio is fundamental for radio engineers also, because they have to know what is coming out of the radio signal. And actually, now this is the radio signal. It's digital, 8 bits, 12 bits, but this is the radio signal. And this is actually what you are going to receive. And how can I do that? Using a logic analyzer that gives you the bit stream in each line of this device. And there are new instruments coming up on the market. One is vector signal analyzer. This is good because it allows you to see the modulation pattern, the spectra, and so on. Again, the problem with VSAs, vector signal analyzer, is that is an analog instrument, is not a digital instrument. And you have also real-time signal analyzers. This is quite new. And what is a real-time signal analyzer? It gives you a very interesting thing. Let me try to explain this briefly. You know GSM? You are familiar with GSM signals? Yes or no? You know that GSM goes up and down. So if you measure GSM in a phone, your phone will go up, transmit, and sleep. Go up, transmit, and sleep. So it's, if you want, TDD system, so time division duplex system. So it goes up, it sleeps, goes up, sleep. Try to measure that with a spectrum analyzer. You'll see, goes up, you don't see nothing, okay? Why? Because a spectrum analyzer actually gives you an average value of the spectrum. It doesn't give you instantaneous spectra. And what a real-time signal analyzer does, okay, here we can enter a lot in signal processing, but what a real-time signal analyzer does, it does something that is called a short-term Fourier transform. You can search in the web. Short-term Fourier transform actually allows you to do the spectra over time. So actually allows you to do this type of graphs, what they call spectrograms if you want, or they call it also waterfalls. So what is this? This is spectra, frequency, this is time. So what you see here is that my signal is doing this in spectra, and here I have a frequency hopping signal. So changing, but over time. This is very, very important for the guys that are monitoring spectra. Extremely important, because they want to know where the spectra is and what it's doing over time. Because it's a TDD system, it's not there all the time. You see, this is quite important, and it's becoming a very, very important instrument in that sense. So let me briefly show you the challenges for the future in terms of instrumentation, and I'm talking about analog and digital coexistence, so software-defined radio. And in software-defined radio, I already told you, I have an antenna, I have an analog part, I have a digital part. And from the analog part, if I have a receiver, I'm a radio engineer, I want to continue to measure the noise figure, the bandwidth, the input VSWR, the gain, the intermodulation. I want to do traditional RF things. But if I go to the other side, then I talk with the digital guys, then they will tell me what is a static gain and offset of my analog to digital converter, what is integral and differential linearity, what is the hysteresis, so strange buzzwords for radio engineers. Okay, and this is actually the problem. We are two roles that should start to talk with each other. So actually, what we can do at this time is we can pick up the analog part and using a vector signal analyzer see its spectra, the time domain and the constellation diagram. But if I go to the other side, I have a logic analyzer and I see a lot of bit streams. Okay, what I can do is, if I convert these bit streams with this formula, I can actually have the digital analog, let's say, information on this side. And if I compare this with that, I can know if my receiver is receiving well the signals or if I have a problem with my receiver. Okay, this is one problem. The problem at this moment is that the devices to do these are not correlated with each other, so I can still have a lot of problems in terms of measurement instrument. So what we come up with an idea, we are designing now what is called a mixed domain signal analyzer. What is this? This is one analog port, one digital port, and it works like a network analyzer, completely like a network analyzer. I can continue to measure the reflection coefficients at the input, I can continue to measure gain. The difference is as the output is digital, the input is analog. Actually, we have, I will pass this one, we have built this system, so this is our analog input, this is our digital stage, and we actually have an instrument there that is actually being built at this moment, and I will stop here briefly. And it's curious that when I look to the time domain of my waveforms, what you see in blue is the input waveform. What you see in red is the digital waveform, which has quantization noise and a lot of other things, but it's a digital version of my input, and this is becoming very, 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 very important. And of course, I will pass this. You know that you have to calibrate our instrument, so I'll pass this fast, because actually we are calibrating our instrument also. The difference is that, as you hear from Agilent colleagues, here you put a short open load at input, short open load at the output, and a through. But now I have an analog to digital. What is a short open load at the digital part? What is a through in a digital concept? So this is actually one of the problems. So what is a tree? And we are working on that also. And we are also working on actually how can we improve the error model in this new type of instrument. So you see that there are a lot of things to discuss here, and I will pass this. I can show you, yes, I can show you here some of the things that we can do with this instrument. So this is actually a software-defined radio front end, where you have a bandpass filter, an amplifier, an attenuator, and an analog to digital converter. And actually what you can see here, you can see the gain of your, let's say, front end, radio front end, and you can also see the phase delay, which is quite important in our case. In our case, we have a problem that we still don't have absolute value of the phase. This is because we don't have a through, but we are working on that. So I told you about software-defined radio instrumentation, so mixed domain, analog and digital. The other mixed domain I have is RF and DC. So what are the main problems when I'm measuring RF to DC? And the main problems, as I said, sorry, let me go back. The main problems, as I said, is that we prove that if we use and if we calibrate our probe with one tone, which is the usual way to do, if we use other type of signals, for instance, in this case I'm using a two-tone, the behavior is going to change. Okay? What that means, it means that I have a completely calibrated instrument, and after I measure another signal and I see the results are different. And so the calibration is useful. Okay? So what some vendors are doing now, they are not selling any more power probes to wireless communication systems. They are selling these new power meters, which is a power meter, yes, but then it has a display that gives you, shows you how the power varies over time. Okay, so you have over time how the power is behaving. So the GSM signal is not giving you an integrated value of power, but gives you instantaneous power, let's say, over time. And this is becoming very, very important in the sense that is more feasible, or you can believe in this instrument because you have instantaneous power, and this is more important for certain cases than the other scenario. So the other problem is, okay, this is a typical energy harvesting circuit. This is the RFID tag. And what is the problem here? You have a lot of diodes around, you have a lot of things. This is nice for a circuit designer that goes to ADS and he wants to spend a lot of time doing this type of circuits. But if you are a system designer, if you want to use all this circuit and you don't want to use this, you want to use a black box model and include this in MATLAB, a good model for MATLAB or Simulink, then you have a problem. How can I extract good models for this? And actually, you can extract good models for this using some mathematical background. Professor Monica here knows a lot more than me about this, but you can actually extract these models in a very, let's say, precise way using nonlinear functions if you want. I will not go deeper inside that. I will show you mainly the instrumentation that can be used, and I heard that this morning you were talking about large signal amplifier, that this is your instruments. So this is Vigo instrument, and actually you can use, this is another instrumentation that becomes very, very important to extract very good nonlinear black box models that you can use and you can give to, let's say, system design engineers. One other important thing about these models is the following. Let me go back. When you design this, or if you go to ADS and you design this in ADS, if you want, okay, what is the problem with this? The problem is that if someone from a company is here, and I give this to the company, okay, my tag, the company designed this and gives this to the customer. This is the tag. If you want, you can simulate it. What the customer is going to do? Okay, I have here the circuit. I can reply the circuit. I can replicate the circuit. So you are giving away your intellectual properties, okay? Because everybody will know how to design the circuit. It's there. You have to copy it, okay? Now imagine that I only give them black box with numbers. Nothing more than this. It's a black box with numbers. I don't say to the person, okay, you have a diode here with a capacitor there that is 10 picofarad. No, I don't say nothing to the guys. I give them numbers. Okay. What is the advantage? They can simulate your circuit, but they don't know what's inside, so you can have your intellectual property in your side. So this is very, very important from this point of view. Okay. And actually, let me go back. And actually, for RFID, another important thing that we are also looking now is how can I measure the overall RFID system? There are only one system I know in a commercial point of view where I can measure RFID. This is a typical RFID, and sometimes I want to know why the RFID is not working well. Is due to the RFID? Is due to the environment? What is happening? So this is another area of instrumentation that we should look carefully. How can we measure a good instrumentation scenario to measure everything? RF to DC conversion, modulation values, what is the air interface, propagation, and so on and so on and so on. There are a lot of information that we still don't have in this sense. So this gives the summary of my first. I hope I was not too fast, and I will give you now 5 minutes, 10 minutes to questions before I pass to the second part.